All right, welcome. Today we're going to pull back the curtain on something that makes pretty much all modern computing possible: multi-threading. We're going to unravel how your computer juggles dozens, even hundreds of tasks all at once, all the way from the basic instructions up to the big architectural blueprints of an operating system. So let's dive right in. So what do spools of thread have to do with any of this? Well, it might seem like a bit of a stretch, but it's actually a perfect metaphor for what's happening inside your processor. See, each thread in your computer is a separate path of execution. It allows a single program to do multiple things at the same time. You can think of it like a weaver who's using many different threads to create a really complex tapestry. Your computer is that weaver, and understanding how it manages all these threads is the key to understanding its performance. So where do we even start? Well, we start with the rulebook, and in the world of threads, that rulebook is often something called Pthreads. Now, here's the most important thing to get straight about Pthreads. It isn't the actual code that makes threads run. It's the specification. Think of it as a standard, a common language that developers can use to tell all these different Unix-based operating systems, hey, I need you to create a new thread, or hey, I need to manage this one over here. This standardization is absolutely crucial because it lets developers write code that can work across a whole bunch of different systems. You know, every thread, just like any program, has a life. It's created, it does its job, and then it's gone. So let's walk through this little story, the life cycle of a thread. This whole life cycle really boils down to a few specific commands. A developer uses pthread_create to kick off a brand new path of execution. Now, if that new thread needs to finish its work before the main one can move on, the main thread calls pthread_join. It basically just sits there and waits. And then finally, when its job is done, the thread can take a graceful bow using pthread_exit. Birth, life, and death, all managed right through this API. But of course, in the real world, things go wrong. That pthread_create call we just talked about, it's not guaranteed to work. You see, a system's resources, its memory, its processing power, they're all finite, so there have to be limits. The call can fail if you try to make way too many threads, or if you give it bad instructions, or, well, if the system just plain runs out of memory. These error codes are the system's way of telling the programmer, nope, can't do that right now, and here's why. So let's ask a fundamental question. Where do these threads actually live? This question brings us to a huge architectural choice in how operating systems are designed, and that's the difference between user threads and kernel threads. This really reveals a massive trade-off. Okay, so on one side, you've got user threads. They're managed by a library inside the application itself, which makes them super fast to create and switch between. The kernel, the core of the OS, doesn't even know they exist. But, and this is a huge catch, if one of those user threads has to stop and wait for something, like say downloading a file, that's a blocking call, and it freezes the entire process. On the other hand, you have kernel threads. They're managed directly by the OS. Now, they're slower to create, but if one of them blocks, the kernel is smart enough to just say, okay, you can wait here. I'm going to let another thread from your process get some work done. So we have these two types of threads, user and kernel. How do they actually work together? Well, operating systems use three main models, or you could call them architectural blueprints, to connect those fast, lightweight user threads to the powerful, robust kernel threads. Let's see how they stack up. First up is the many-to-one model. And honestly, the name pretty much says it all. You can have a whole bunch of user-level threads, but they all have to share one single lifeline down to the kernel. And you can see it right here in this diagram. All those user threads up the top, they're all being funneled down through that one single kernel thread at the bottom. The potential bottleneck here is, well, it's pretty obvious. So what's the good news? It's really efficient. It's super fast to manage all those threads up in user space. But the downsides, oh, they are severe. Just like we talked about before, one blocking call freezes everything. And this is the real killer today. You get no true concurrency on multi-core systems. Since only one kernel thread can run at a time, the process can only ever use one CPU core at any given moment. So as a direct response to all those limitations, we have the complete opposite, the one-to-one model. In this setup, every single user thread gets its own personal, dedicated kernel thread. No sharing allowed. And the difference is just night and day. Look at that. It's a clean, direct mapping. Every user thread has its own body in the kernel, ready to execute its instructions on a CPU core. Now this
This is a powerful model. It gives you true concurrency, which means a single program can actually run on multiple CPU cores at the exact same time. And if one thread blocks, no problem, the others just keep on running. This is the model that modern operating systems like Windows use, and it makes perfect sense, right? For a desktop OS, responsiveness is king. You don't want one tab to freeze your whole browser. But what's the downside? It's expensive. Creating a whole kernel thread for every single user thread, that carries a lot of overhead.
So if the first model is too restrictive and the second one is too expensive, is there a compromise? Well, that brings us to our third option, the many-to-many model, which really tries to get the best of both worlds. The key word here is flexibility. You've got a pool of user threads, and they're mapped onto a smaller, or maybe equal-sized, pool of kernel threads. The operating system can then dynamically manage these connections, assigning kernel threads to user threads whenever they're needed. This model offers a pretty great balance. It allows for concurrency without that heavy overhead of the one-to-one model. But its greatest strength is also its biggest weakness. This whole dynamic mapping thing is incredibly complex to design and get right. And because the number of kernel threads can be less than the user threads, you aren't always guaranteed to get true concurrency. Okay, so we've been deep in the technical weeds with these blueprints. But why should you actually care about any of this? Well, because these low-level decisions have a massive impact on your day-to-day experience with every piece of tech you use. At the end of the day, the choice between these models directly affects everything you do. It's the reason your web browser might freeze up completely when one tab is loading a heavy page. It's what determines how smoothly your video editor can render a file in the background while you keep working on something else. This stuff is the absolute foundation of performance in the multi-core world we live in. And that leaves us with a really fascinating question for the future. As we move towards CPUs with massive core counts, dozens, maybe even hundreds of cores, the overhead of that one-to-one model becomes a bigger and bigger problem. But at the same time, the limitations of the many-to-one model become even more crippling. So will the complex many-to-many model make a comeback? Or will we see entirely new architectural blueprints emerge to manage the threads of tomorrow? It's a question that engineers are grappling with right now. Thanks for watching.